Hello. Today I'm going to discuss a particle in a one-dimensional box. So this is a special case problem. Particle in an infinitely deep one-dimensional potential well. So here we need to calculate the eigenvalues and eigenfunctions of uh, this particle. It is there in deep inside infinite potential well. So topic name is particle in one-dimensional potential box. Potential box. So this is infinitely deep one-dimensional potential box. Potential well. Okay. Okay. So here I'm going to consider one potential box like this. This is potential box or potential well. Okay. Here I'm considering a particle. The mass of this particle is m. It moving along x-axis, remaining two axes, which means y and z are restrictions. So this particle is moving along x-axis. So in this infinite potential well. So let the origin begin at one corner of the box. And the x-axis is perpendicular to the opposite walls. So for example, here I'm taking the length of this box. I mean, this distance from here to here, this one corner to another corner. This length is, let to take this one. This length of this box is this length of this box from starting this corner to this corner. Like to give this small a between the walls. So the motion of the particle along the x-axis is conformed between these two walls, x equal to 0 and x equal to a. Or in some box we can take x equal to l also, the length of the box. Here I'm considering x equal to a. Okay, this is a infinitely deep one-dimensional potential well. So the height of these uh, walls are infinity. Infinity. So this is also infinite height. Suppose inside the box. So what is the reason of inside the box? Uh, 0 less than x less than a. This. So there is no force acting on the particle, so that in this region the potential energy, which means V of x is 0 because of force free particle, right? Potential energy is uh, depends upon position of the particle. So x is equal to 0. When this particle collide with the perfectly this rigid walls, uh, there is no loss of energy. It is purely assumption. Okay, here there is no loss of energy between the collisions of this particle and this wall and this wall during the motion. So there is no loss of energy. The total energy of the particle E remains constant. Okay, in order to leave the region, the particle will have to do an infinite amount of work. It is considerably impossible. Guess if this particle is coming out of this box, this particle want to do infinite amount of work. It is impossible to come outside this box. Therefore, we can confirm this box is there in between the x is equal to 0 and when x is equal to a region. Then we can write this one is so less than x less than a. So here I'm going to apply the Schrodinger wave equation. We already know Schrodinger wave equation. So simply I'm going to take the Schrodinger wave equation here. That is very crucial thing. So we already know this Schrodinger wave equation, right? D square psi divided by the x square, because we are dealing with the simple in one dimensional, right? Plus 2m divided by h cross square e minus v of wave function psi is equal to 0. This is Schrodinger time independent wave equation. Here the v of x is equal to 0. We already discussed potential energy is equal to 0. Then this equation becomes like this. So put v equal to 0 here, v equal to 0. Then we can get this equation d squared psi divided by dx square plus 2m divided by h cross square e into wave function psi equal to 0. So then I'm going to consider this one as constant, which means k square is equal to 2me divided by h cross square. So therefore I can write this equation like this: wave function psi divided by dx square plus the k square wave function psi equal to 0. Okay. So this equation I'm going to consider the equation number 1. Okay. So the solution, this is a second order differential equation, right? The solution of this equation, wave function psi of x equal to a sine kx plus b cos kx. So where a and b are constant of integration, we have two boundary conditions. One is in case if you observe clearly, two boundary conditions are there. The one is first boundary condition at x equal to 0. Okay. Second boundary condition x equal to a. Then I'm going to write this at x equal to 0, wave function equal to. Did you understand this information? Why is wave function equal to 0 at boundary? I already told you. Particle is there inside the infinitely deep potential well. What does that mean? The particle will not come out of this box. It is impossible because this height of this wall is infinity. So in case this particle is coming out of this box, this particle must be do some work infinite times, right? That is impossible. Therefore, the particle is confirmed in between the two walls. There is no wave function this outside the box, which is why I am considering wave function psi is equal to 0 at boundary conditions, which is why I'm giving wave function equal to 0 at two boundary conditions, right? Okay. Now you can apply these boundary conditions to this equation, the solution of second order equation. So then you can get some information. So in case if you try to apply the first boundary condition, x is equal to 0, right? X is equal to 0, sin 0 is equal to 0, cos 0 is equal to 1. So therefore, I got here, if you apply the first boundary condition, this first boundary condition, right? In this equation, get um, it is better to write from the first boundary condition. Okay. So in case if you apply first boundary condition, 0, a sin k in place of x0 plus b cos k in place of x equal to 0 or 0 is equal to 1. So therefore I got here b equal to 0. B equal to 0. Okay. Now you can substitute this equation. It's better to give mention some equation number. This is equation number 2. Okay, this is equation number 3. In case if you try to substitute equation number 3 in equation number 2, then you can get this equation, right? Substitute equation number 3 in equation number 2. So then you can get a solution where function phi of x is equal to a sin kx. Now you can use secondary bounding. Okay, this is equation number 4. Equation number 4. Now you can use the secondary bounding condition. Use second condition. What is the second condition? Wave function 0, x is equal to a. So second boundary condition like this, right? This is a second boundary condition. Wave function is equal to 0 at x equal to a. So it is better to write like this. X is equal to a and x is equal to at x is equal to a, wave function equal to 0. So therefore we can use this secondary boundary condition in equation number 4. Okay, then you can get like this: a sin k into 0. Sorry, a, right? X equal to a. So then sin ka equal to 0. Then what is ka value? So we know sin theta equal to 0. Okay, what is the theta value? Theta is equal to n pi, right? Every n pi value. Here theta is equal to n. Okay, so by using this equation, I'm going to write the equation like this. This is the main equation, right? After getting the sin k equal to 0, then k is equal to 0, then what is the theta value here? K, this is sin theta is equal to 0. What is theta value here? Ka. So that is n pi, right? Then I can use this one. Or else, in better words, this is maybe you can take equation number 5. So equation number 5 satisfy the one condition is there. So that is uh, satisfied only when Ka equal to n pi. Then you can search the K values. You can get some answer. Maybe Eigen value equation of K function. So what is K value here? The K equal to n pi divided by a. Okay. We can't take n is equal to 0. Okay. When in case, for example, in case if you use n is equal to 0, then k is equal to 0, you can get e is equal to 0. What does that mean? Hence the wave function becomes to 0 everywhere in the box. Okay, that is not there, right? So this means that the particle with the 0 energy cannot be present in the box. That is, a particle in a box cannot have 0 energy. Hence the wave function for this motion, I mean 0 less than x less than a, is given by like this. So if in case if you try to put this k value, this is equation number 6, somewhere it is equation number 4. Substitute equation number 6 in equation number 4. Then you can get this answer. Phi of x equal to a sin kx. In place of k, you can use k value. That's it. A sin in place of k, n by x divided by. Now I'm going to find the Eigen values of this uh, equation. So we know the k square equal to equal to 2me divided by h class square. Somewhere it is there. Here from starting, k square is equal to 2me divided by h class square. Then here I got equation number 6, k equal to n pi divided by a. So by using these two equations, I'm going to write these two equations like this. 2me, sorry, this is k square, then I can use remove here, k, now it is correct, right? H cross square, this is k, this is k, I'm going to equal these two equations, root n pi divided by a. Okay, so then you can square both sides. This will get here 2me divided by h cross square equal to, this is n square pi square divided by a square. So then e equal to n square pi square h cross square divided by 2m a square. So these are the eigenvalues of infinite potential value of the particle. So here this equation shows that the eigenvalues of energy are discrete, which means not in continuous manner. These values are called energy levels of the particle. Energy levels of the particle. So in case if you try to put n is equal to 1, 2, 3, 4, and so on, you can get the and in case if you try to put n is equal to 1, you can get ground state, next exit state, or next exit state, we can get, okay, n is equal to 1, 2, 3, and so on. You can get a different type of energy values. N equal to 1, 2, 3, and so on, etc. So here n is the number, n is equal to 1, 2, 3, 4, and so on. The pi, pi square value is the value, h cross is modified constant value. 2 is a number, m is the mass of the particle. Here the one function is changing, uh, the length of the box a square. In case here this length of the box is increase, energy level of particle will decrease. So therefore, in case we try to substitute n equal to 1 here, then you can get here, right? This is n particle. Then I'm going to use n is equal to 1. N is equal to 1. Then I can get pi square h cross square divided by 2m a square. N is equal to 2. N is equal to, then I can write like this equation. En equal to n square into E1, right? Then you can use this equation. So therefore, the energy level of these particles are like, and this is infinite potential box. Okay, this height is infinity for assumption. So this is 0, this is 1, n equal to 1. Then what is energy level here? E0 and E1. N equal to 2. Then you can get here E2 equal to 2 square E1, right? N equal to 3. N equal to 3. Here I didn't write n equal to E3 equal to 3 square E1. Okay, these are the eigen values of infinite potential box. Okay, next we are going to find out the eigenfunctions corresponding n eigenvalues of the particles. Okay, so we know wave function of this one-dimensional infinite potential box. We already get this equation. Wave function psi of x equal to a sine kx, kx, right? This is the wave function equation. Wave function for the motion of the particle. So in the region 0 less than x less than a, okay, so wave function is equal to psi n is equal to 0 at two boundary condition, x less than a or x greater than a condition. So I want to find this, what is this constant value, a value. So this constant, for that I'm going to apply the total probability that particle is somewhere in the box must be unity. Therefore I'm going to apply the boundary condition. So this is integral 0 to a, okay, psi star psi dx equal to 1. So this psi star psi we can write like this, right? Integral 0 to a modulus of modulus of psi star square, modulus of psi square, not star square, equal to that. Then what is this wave function psi? Psi equal to a sine n pi x divided by a. So we try to put why I am using 0 to a. The boundary condition particle is where is that 0 to here also we can write x is equal to 0 to x is equal to a. So this is the limits x is equal to 0 to x is equal to a, which is why I'm using 0 to lower boundary condition 0, upper boundary condition a. Then you can apply this wave function here. So a square sine square n pi a divided by. So integral 0 to a square sine square n pi x divided by a into dx equal to 1. If you clearly observe here, the sine square is there. So I'm going to write this a square outside the integration because this a square constant 0 to a sine square n pi x divided by a into dx equal to 1. I'm going to use the one trigonometric formula. I know 2 sine square theta equal to 1 minus cos 2 theta. So then sine square theta equal to 1 divided by 2 into 1 minus cos 2 theta. So this is sine square theta, this one, right? This is sine square theta. So therefore, a square integral 0 to a 1 divided by 2, 1 minus cos 2. This is theta, right? 2n pi x divided by into dx equal to 1. A little bit calculation is there still. I'm going to writing this step here. Okay, one more. A square 1 divided by 2 also I can write outside. Remaining 0 to a. This one is dx, first one, minus integral 0 to a cos 2n by x divided by into dx equal to 1. So therefore, if you try to apply the integration, then you can get here this is x, okay, which means 0 to a. Here this is cos, integral cos theta sine theta, first sine theta. I'm going to use this one, okay. What is theta? This one, 1 divided by, right? So reciprocal of this one, a divided by 2 pi n. So this is also limits 0 to a. So in case if you observe clearly here, so if you observe 0, 0 you can get, if you observe a, this entire time term is going to be 0, then finally you can get here only x value. So therefore the final equation a square divided by 2 into small a, that is equal to 1. So in case if you want to avoid this confusion, small a to capital A, then you can use x is equal to L. Okay, x is equal to L. Therefore, here a equal to, I can get a equal to 2 divided by small a. Therefore, total wave function of the one-dimensional infinite potential well, root 2 divided by a sine n by x divided by a. This is the total wave function. This is the total wave function. Therefore, the first three wave functions are like this. This is first wave function. Psi 1, x is equal to 0, x is equal to a. This is psi 2, psi 2. This is psi 3. Okay, psi 3. This is psi 2. Okay. So it is evident that psi 1 has two nodes, right? Two nodes, x is equal to 0, x is equal to a. Okay, a divided by 2 also. Okay, a divided by 2. This one is a divided by 2 right in the middle. So a divided by 2. And the wave function psi 3 has 4 nodes. One is x is equal to 0. I mean x is equal to a divided by 3, x is equal to 2a divided by. So I'm going to write this equation like this. Psi 1 has the two wave function, this psi 1, psi 1, psi 1 has two nodes at x is equal to 0 and x equal to a. Okay. Psi 2 has similar thing. Psi 2 has this x is equal to a and this x is equal to 0. First one, x is equal to 0, x is equal to a divided by 2, right? Psi 3 has 4 nodes, x equal to a and x is equal to 0, x is equal to a divided by 3, x equal to 2a divided by 3. So therefore, how many nodes are possible and wave function? Yes, if you try to observe here clearly, then you can get answer. N plus 1 nodes. N plus 1 nodes. So this is all about Schrodinger one-dimensional infinite potential box. And here we are using uh, normalization condition, right? That is a probability of particle finding normalization condition. This is right. What happen if you use a orthogonality of wave function? What happen in case if you use the orthogonality of the wave function condition? Then you can get the answer the 0. So both term x equal to 0 and x is equal to a. Then you can get equal 0 to wave function. In case two different wave functions are there, then you can use orthogonality condition wave function. Then you can get 0. So why I'm going to discuss this simple one-dimensional infinite potential box. In case if you want to find different type of probabilities, first you need to practice one-dimensional infinite potential box. So here I'm going to raise one question to related to GATE CSN and just exam. So maybe you are all aware of these things. So what is the expectation value of this position? You can use the same condition, same wave function. What is the expectation value of the position square? What is the expectation value of the momentum? So in case if you want to find this thing, then I'm going to ask one more question here, different type of question. The potential energy they are giving like this, right? Potential energy they are giving like this. This is x is equal to 0. This is x is equal to a. So in case if I cut here half of the box, then what is the probability here? X is equal to a divided by 2. So then I'm going to using some boundary condition here like this, n boundary condition. So then we need to find each and every potential energy between the two walls. Then we want to find the total uh, probability of the particle. So for example, I want to find the particle probability between x is equal to 0 and this position. This position, I don't know this position value. Okay, so I can divide this one, or else I can say this equation I'm going to write exactly in CSA net and gate forms uh, like this. So maybe you are all aware of this. Then I'm going to use this equation like this. Just wait to explain this thing clarity. Okay, fine. This is potential box, given potential box, right? This is infinity, this is infinity. So for example, this is x is equal to 0, this is x is equal to a. So exactly I'm going to cut this box into, I mean, one more wall is there here. This is a divided by 2. So then again I'm going to use this box here, one restriction here. So this is a divided by 4, this is a divided, sorry, this is a divided by 2, this is 3a divided by 2, right? 3 by 2 here, right? This one. So this is perfect. Then we need to find the expectation value, which means what is the probability between the x is equal to 0 and x is equal to a divided by 2. Then you can find the wave function amplitude. And then one more condition. What is the expectation? I mean expectation value and the probability of the particle motion in between two boundary conditions, x is equal to a divided by 4, x is equal to a divided by 2. Like that, you can practice each and every step. Then you can understand how to calculate this expectation value, probability value by using this boundary. So actually what happened in CSR net and gate examinations, they are giving the different type of potentials. Okay. In case if you try to observe these quantum mechanical questions, clearly either they are giving potential energy, most of the cases they are giving potential energy or wave functions. Then they are asking to find something, probability and expectation value, what is the energy value, what happen if some perturbation is there in that conditions. They are framing according to their own perspectives, right? Then we need to practice this type of questions to solve the critical questions. This is very simple question. So normally in CS or get net, and they are not on, maybe they are not asking this type of simple questions. So their framing questioning is very difficult is there. For that we need to achieve the difficulty level. So initial stage onwards, we need to practice this type of problems. Then only we can get the potential to solve the CSI problem.